Okay, so this is empirical formulas and molecular formulas. Now, first thing, what's an empirical formula? Empirical formula has the lowest possible numbers in a formula, okay? And a molecular may or may not. Now, what does that mean? What that means is that a molecular formula can be the empirical formula, but it doesn't have to be. And here's an example. If we take glucose, which is C6H12O6. That's its formula. This is a molecular formula. Why is it a molecular formula? Because it doesn't have the lowest possible numbers, the lowest possible whole numbers. And so I can divide all these numbers by 6, and I can get CH2O. And this would be the empirical. Okay, so the top one, C6H12O6, is molecular. The bottom one's empirical. Now, how do you find these? Well, you find these molecular formulas and empirical formulas. You can find them experimentally, okay? An empirical formula usually comes from element analysis. And in that case, you get percents of each element, okay? Now, the molecular, you find, number one, you find the percent. To get the empirical, but then number two, to get the molecular, you have a second experiment to get the mass. And I'm going to show you how that. So to get the molecular, you have to actually do an elemental analysis to get the percent carbon, percent hydrogen, percent oxygen, and you get an empirical formula out of that. And the molecular, you do a second experiment to get the actual mass. How much does the molecule weigh? And both of those are independent of each other. You can find a percent, but you don't know the mass. You can find the mass, but you don't know the percent. But if you put them together, you get the molecular, okay? And I'm going to show you how to do this. So first, let's just go through empirical formulas from analysis, okay? Okay. And so typically what you'll have in any sort of problem is we'll say something like after analysis, it was found. Notice I'm using third person passive like you should be using in your lab reports. It was found that we have, let's say, 55.0%, and this is all by mass, of carbon, and let's say 25% of hydrogen, and let's say that we had the remainder. Let's see, that'd be 20. It's got to add up to 100, by the way. So that'd be 2580, and we'll say 20% of chlorine. Okay, and let's see, that's 45. So that all adds up to 100%. And let me go ahead and make this out to be 3 sig figs. So that'll be 25.0%, and then we'll have 20.0%. I'm just changing those just so we're consistently 3 significant figures all the way across. Because remember, any calculation you do, you're going to have to use sig figs anyway. So here's the procedure. What we're going to do is we're going to find the relative mole ratio between these guys. Okay, so the first step, though, is you convert your percentages. Just go ahead and take your percentage and just rename it as grams. So this becomes 55 25.0 grams of carbon. And that 25% of hydrogen becomes 25.0 grams of hydrogen. And that chlorine becomes 20.0 grams of chlorine. Now, the idea is that you're out of 100 grams. Okay, that's what it means to be a percent, is out of 100. And so by doing that, we're making sure it all adds up to 100 grams. Okay, and so the next thing you need to do is find out how many moles you have of each one. And as I showed you in a previous video, the way to do that, matter of fact, why don't we just go ahead and reset it over here so we can have some room. And if we look on the periodic table, underneath the element for carbon, we see that a mole of carbon is 12.0 grams. Keep in mind that generally we're going to go out one decimal place. Now, if you go out extra decimal places, like 12.011 grams, which is on the periodic table, it's okay. It's okay, but you'll still have 3 sig figs with 55.0. Okay, so we go ahead and put that in our calculator, and we're going to get the number of moles. And so we say 55.0 divided by 12.0, and I get 4.58 mole carbon. And keep in mind, as we're doing this, we're going to make sure that it's not just grams, it's grams carbon. We're going to make sure it's not just moles, it's moles carbon. Always label everything with what it is. Okay, and so the second thing we're going to do here is we're going to go ahead and do hydrogen. We say 25.0 grams hydrogen. We'll draw a line, draw another line. These are all dimensional analysis problems, they really are. And we're going to say from our periodic table that a mole of hydrogen is 1.01 grams hydrogen. And I'm not going out one. Hydrogen is the only one that I make an exception with when I'm doing these, going out one decimal place. And the reason is that I just want to keep 3 significant figures. That's the only reason why I go out 2 decimal places on the hydrogen. And so we do that, and we put this in our calculator, and we're going to get 25.0 divided by 1.01, and that gives me 24.8 mole hydrogen. Okay, and then finally we're going to go ahead and do the chlorine, and so we say 20.0 grams chlorine, and we draw a line, we draw another line, and we look on our periodic table and we look for chlorine, and chlorine, I believe, is 35.5. Yes, it is. It's 35.5 if we round to 1 decimal place. 35.5 grams chlorine for every mole. And, of course, this is grams per mole, but we flip them over. And that gives me, I'm going to put that in my calculator. And let's see, we get 20 divided by 35.5. And, all right, good. And let's see, and we get right about half a mole, 0.563 mole chlorine. Okay, so now we figured out how many moles we have in this sample. Now, the next step is we'll move this over a little bit, is we need to divide by the least number of moles. So I want to divide by least moles. All right, and what's the least moles? The least moles is the 0.563. And so we're going to divide everything by 0.563. So we divide by 0.563, we divide by 0.563, and then finally we divide by 0.563, and we put all of these in our calculator. Of course, if you divide by the same thing, you're going to get 1.0. And so we have 4.58. We're going to divide by 0.563, and I get 8.1. generally for the final answer here, because these are ratios that we're doing here, the ratio of each one to each of the others as far as moles, and we got 24.8 divided by 0.563, and I get 44.0. And it's a ratio, so there's no units here. And so now we can finally go ahead and get our empirical formula. And so our empirical formula would be, we take each piece and we add it to the formula. So we go carbon, hydrogen, and chlorine, and we're going to take each piece from the ratio. So that 8.1, we're going to round to 8. And so that becomes C8. You always write. Now remember, formulas are counted quantities of each element. Okay, and so that 44.0, it rounds to 44. And that 1, well, it rounds the 1, and there's an implied 1 behind that chlorine. So our final empirical formula is C8H44Cl. Okay. All right. So there's one empirical formula that we determine given the original percents. And that's how you do it. So let's go ahead and do another example from percentages. And let's say that we were told that we had, let's say 75.0% copper and 25.0% oxygen, some sort of copper oxide. And so we do it the same way. So we say, and I'm going to start over here on the far left this time. And so we say 75.0 grams of copper. And we say 25.0 grams of oxygen. So you just go ahead and convert the percent immediately to the same number, but you put a grams behind it. Obviously, if you're given grams, you need the grams to add up to 100, and usually you do, or you can do a ratio to get it to add to 100. And so we'll go ahead and let's find out how many moles we have of each one. And so I look on my periodic table for copper, and I find that copper has a molar mass of 63.5. And so it's 63.5 grams copper for every mole copper. Molar mass of copper I got off of the periodic table, and it's 62.5 grams per mole. That's what that number means. And we'll go ahead and put that in our calculator. And here we go. And so we say 75.0 divided by 63.5, and I get 1.18 mole copper. Now we can do oxygen. And it is, and I look on the periodic table and I see that a mole of oxygen is 16.0 grams oxygen. And we put that in our calculator. And so we go 25 divided by 16, and I get 1.56 mole oxygen. Now, we're going to divide by the least number of moles. What's our least number of moles? Least number of moles is the 1.18. So we're going to divide everything by 1.18. Hold on, make sure no one's waiting outside. Nope. Okay, 1.18. And that's obviously equal to 1.0. And we'll divide by 1.18 down here as well. And we put that in our calculator. And so we say 1.56 divided by 1.18. And I get 1.32. Or we'll just go out one decimal. Okay, and so what we have to do is we have to round. Now, when we start getting, as long as we're 3 or less, we just go ahead and round it down. And I'm going to show you something here. And so we have copper is 1, and we have oxygen is also 1 because it will round down. Now, what do we do in a situation where we have this going on? Let me put a hypothetical situation. This is hypothetical. Okay. In other words, it's not a product of any of the calculations over here. But let's say we had, after we were done, we had 1.0 and let's say 1.5. Now what? Well, you would not want to, usually you would not want to round that to 2. The reason is because you can have an odd number. In this case, this tells us that it's probably odd. Okay? And so what we'll do is we'll multiply everything through by 2 to get rid of that 1.5 and turn it into a whole number that's pretty close. And then we'll round from there. Times 2, times 2. And if we say times 2, we're going to get 2.0 and 3.0 if hypothetically we'd end up with a 1.5. And so now we have a different compound, and that would be copper 2 and a 3 on the oxygen. Okay, so if you end up being somewhere between, I would say, 1.4 to, I don't know, let's go 1.7, I would consider multiplying times 2. Now, strictly speaking, though, what you could do, but for these problems, it's going to be, they're going to be obvious when you're working problems either on homeworks, tests, or quizzes. It'll be obvious. It'll be either you get 1.0 and 1.0, or 1.0, 2.0, or you get, over here in the green, 1.0 and 1.5. For problem purposes, it won't be, kind of, I'm not sure whether I should multiply by 2 or not. Okay, so keep that in mind, that if you run across where you have in the final result, not over here though, I mean, that's 1.5, I know, but we still have to make it over here. Okay, and 1.3 is close enough to 1 that you would just go ahead and round it to 1. Okay, but if you're getting close to 1.5, that's when you could consider doing it that way, where you just multiply everything through by 2. Now, it turns out that there is online, there's an app for everything, right? There's an app for everything, and you can actually go online and do empirical formulas. Empirical formula calculator. There it is. See right here? There it is, Omni Calculator. And there, that's not it. Hold on, I was just looking at it. Empirical calculator, chemistry. Here it is. There it is. Okay, that's in Sydney, some university in Sydney, and we can do the same thing where we have 75% carbon, and let's say, oh, let's just make something up. And how about say 15% of say hydrogen, and let's say we had, whoops, I got it backwards. Say 15% hydrogen, and then the remainder was oxygen. And so we would say, let's see, that's 90, so the rest of it would be 10% for oxygen, and then it'll calculate it out for you. And you can see it gives you a final answer down here based on variance. Okay, and according to this calculator, it's C50H119O5. Pretty cool. You don't have to do the calculations, but obviously when we're taking our test this is not something that's going to be available to you. But it is one way to check, your empirical calculation. So strictly speaking, what this one is doing is it's trying to find the best fit. And so it's not necessarily rounding the numbers like I just showed you. Okay. But generally, you want to go ahead and follow this procedure right here to do the same thing, with like copper and oxygen. Okay. So there's another way, and it's the way we're going to do our experiment, or when we do lab. And the way we're going to do that, and if you've already done the lab, then don't, this is what we did. And let's say we have an experiment where we have, let's say, 1.898 grams of copper. And then we cook with excess sulfur. And what that means is that you have more than enough sulfur to react with the copper, and we form let's say, 2.304 grams copper sulfide product. And we want to know, what is the empirical formula? How would we go about doing that? Well, here's the thing. It's pretty much, you have to take advantage of what's called the law of conservation of mass. Now, I know how many moles, and I know how many grams copper I have, so I can know how many moles that I have. So I can get that very easy. The question is how many moles of sulfur do you have? And where do you get that? Well, we can go ahead and say, I have 1.9898 grams of copper, and I can go ahead and get the moles from that, okay? Because we're doing empirical formulas. Remember, we get the moles, and then we divide by the least number of moles. And so I'm going to go ahead and put this in the calculator for copper, and the molar mass of copper is 63.5. So it's 63.5 grams copper for every mole copper. Okay, so we can go ahead and get that because I know how many grams copper, because I went to the scale, I put it on a scale before I did the reaction. And so we got 1.898, and that's divided by 63.5, and I get 0.0299, 0.0299 mole copper. Okay, that was easy peasy. But how do you know how many moles of sulfur you have? Well, if you go from 1.898 grams to 2.304, that extra mass has to come from somewhere, and it came from the sulfur that you reacted with it. So we say, I have 2.304 grams of some sort of copper and sulfur, and if I subtract off the 1.898 grams of just the copper, what's left over? The sulfur. And so I do that, and I say 2.304 of the product minus 1.898 grams of the copper, and that gives me 0.406 grams of sulfur, because that is where the sulfur came from. Now I can go ahead and find the moles of sulfur, and a mole of sulfur is 32.1 grams of sulfur. For every mole of sulfur, there's the molar mass. And so now I can say 0.406 divided by 32.1, and I get 0.0126 mole of sulfur. Now I'm ready to get the mole ratios between the two so I can get my final formula. Okay, did y'all see how I got that? You see, the thing that you have to realize is that the copper sulfide is not the sulfur. It's the copper and the sulfur. And so if you just subtract off the copper that you started with, because that doesn't change. I mean, you're not gaining or losing any copper. You just subtract it off. Now we can get the grams of sulfur, and using the molar mass of sulfur, we can get the moles. And so now I can go ahead and divide everybody by the least number of moles, and that would be 0.0126, 0.0126. And of course, that becomes 1 down here. And so now I can say 0.0299 divided by the least number of moles, and I get 2.4. Remember what I was saying about, if you're like 4-ish or 6-ish, that you need to go ahead and multiply everybody through by 2, because it tells you that one of them is odd. And so what we're going to do is we're going to go ahead and multiply everybody through by 2, only because this is close to 5. So we don't round. Okay, that's only the case for that. Now, if it had been 2.3, I'd just go ahead and round it to 2. But it's not. And so we would say times 2 gives me 4.8, and then that rounds to 5. And that times 2 gives me 2. And so that tells me the final copper product is maybe it's Cu5S2. Now that's a pretty odd compound, because generally speaking, copper comes in 2 flavors, copper 1 or copper 2. But that's what you get. Experimentally, you may or may not get something that lines up with what we already know. Okay, chances are what you really had was copper 2. There you go. Chances are that's what you really had. But that's not what we're going for. So what's the upshot of all of this? So you're still using, you still got to find the number of moles, but once you have the grams, you can go ahead and get the moles. And how do we get the grams of the sulfur? We just take a difference. And then you can go ahead and get the least number of moles, divide by whatever that is, and then go from there and get your empirical formula. So that's how you do empirical formulas from an experiment. Okay, this is one way of doing it, and that's what lab 3 or whatever number lab that is, and that's what we do when you find the empirical formula for copper sulfide product. And like I said, there's really only 2 kinds of copper. There's copper +1, copper +2, and you really should get either copper Roman numeral 1 sulfide or copper Roman numeral 2 sulfide. But experimentally, you may come out a little different. Okay. All right, well, that's empirical formulas and how to calculate them. And so I'm going to go ahead and turn off the recorder.